And I think the truth table should be in this group logic and bit operations. So this is the truth table. You can just input the matrix here. So in this case, we can easily set up a system like this. So now let's consider rectifier system like this. In books, you will see that if you use this kind of three-phase switches, you can convert a three-phase voltage into a DC voltage like this. And this is the load. So this is the one always used. The circuit always used in, I think, in power systems textbooks. And what is the actual DC voltage? What it should like? The DC voltage may not be straight line. It should be given as a signals like this. So these are the results given in textbooks. And there are a few things we are not quite certain. We just, if we learn the courses like this, we have to trust the results. And we cannot analyze on our own if we do not use software. What is the load of the system changes? What shape of the converted signal would like? And if the trigger angle is changed, so what signal will be like? And what are the characteristics of the element? For instance, the latches changes. What will be the output of the system like? We need to solve this kind of problems by the use of simulation technique. So how can we perform simulation for this kind of systems? If we go back to the power systems block, we will see that there are quite a lot of power electronic devices. And this one is the one I want to demonstrate here. We can use a three-phase input here, and we can use the gauge signal to control it. And then this should be the output of the signal, and we can connect load to it and to observe the final results. Alternatively, if we use these two parts as input part, and these are as the output part, then we are performing inverting process to transform a DC signal into a three-phase signal. We do it like that. So we can use this block to perform simulation to our own problem. A2B. This is the model I created earlier. And in this model, this is a key component. And we have a three-phase input here. And then we can connect the three-phase input and also the pulse generator to this one. And this one will give the trigger angle. And then we should have an output, DC output like this. So we can display the final result. Also, we can connect it to a load. The other one will be better. So this is the system, the input and the load. And we can observe the DC output here. And we can perform simulation to this kind of problem. And finally, we should get the result. And the right one should be the DC signal we expect. And we can change the trigger angle here. If we change it from 50 to something smaller, 15, then we can visualize the result like this. So this is supposed to be the DC circuit, the DC signal. So now let's consider a more complicated thing. The double loop DC motor drive system. And in the system we have two loops. One is the current adjusting loop, and the other one is the speed adjusting loop. And there are PI controllers implemented by operational amplifiers. It seems to be quite complicated. And in control process, normally we will model the whole system by linear blocks. For instance, this part by a block like this, I think. For the thermistor part, it will be approximated by a linear component like this. And for the motor, they usually model like by a linear part like this. And I have demonstrated that for linear systems, the result might be misleading if we, so for this kind of systems, the result may be misleading if we use linear part to represent the original system. So how can we model the original system with proper blocks defined in simulink? So let's go back to the same power system block, and we can see that there are motors in it. There are DC motors and AC motors, different kind of AC motors. We can use this motor, blocks directly. And now, for the system like this, we can use the simulink to express the original model. DC motor. So this is the system modeling I want to use here. And in the system we have a motor block here. And the heuristic converter. Here just to use a conventional linear PI controllers, but they are not quite accurate. So for this kind of system, you can easily perform simulation and see the control result. If the control result is not satisfactory, then we can tune the parameters in the system. It's rather slow. So this kind of signals are similar to the ones that you find from the real experiment, I think. So these are the electrical devices.